every isolated solution to f of c equals 0 is an endpoint of some solution path in the homotopy H. So as t goes from 1 to 0, I can track solution paths, starting at all the solutions for the easy system G. And the theorem is, in fact, we get all solutions to F at the end of the track, provided that G is general. Okay, so that means random coefficients. Sufficiently random. And that's what's going on here. So here, we started with F. It's a hard system. We design a G, similar enough structure and general enough. These solutions we can oftentimes trivially write down, and then as t goes from 1 to 0, we track the solutions numerically using a predictor-corrector method, more or less Newton's method.
And you can estimate the errors?
You can estimate the errors. So in fact, there are certified trackings that are available, although they're slower. What's usually better is to just track without regard to the error, and then after the fact do a verification, which is also possible. You can provably verify. Yes, Smale and Shube actually developed a technique to check that you're within the quadratic zone of convergence for Newton's method. Yes?
And some of the solutions come together?
Yeah, so different things can happen during the track. So solutions can come together, and that would represent that this solution has multiplicity. Or some solution paths can diverge to infinity. In particular,
if you projectivize, are you able to salvage those?
So this technique works best in affine space. So these are actually just spurious. These are really not solutions. Okay. The key is that G has at least as many solutions as F, and we get all the solutions of F by tracking. That's really what we want. Okay, so this is a powerful technique, actually. Okay. Let me say what I mean by, let me be precise about what I mean by point line correspondences for 3 views. So as we saw with 2 views, 3D reconstruction uses points and photos that match. For 3 views, we can actually use lines as well. So let me call the elements of P2 image points and the elements of P2 check, or P2 dual, image lines. And elements of P2 disjoint union P2 check times 3. Here I'm interested in 3 views now. This will be a point line image correspondence. So it's a choice of point or line in each image. So for example, something in P2 times P2 times P2 dual, this will be a point-point line correspondence. So what does it mean for the line to correspond with the points? So definition, a calibrated camera configuration ABC is consistent with a given point line correspondence if there exists a point in P3, a world point, and a world line, a line in P3, containing that point, such that A, B, C respectively map these to the given points and lines in P2. That's it's crucial to understand what it means for lines and points to match. Maybe a picture helps. So 3 images. Let's say I have a point here, and a line here. What does it mean for these all to match? it means that there's a point to match under A, B, C. It means that there's a point in P3 and a line in P3 through the point, such that A maps this point to the image point, B maps the point to the image point, and C maps the line to the line. Okay. Any questions about this? Okay. So here's the main result. So this is really experimental math here. The rows of the following table display the algebraic degree for 66 minimal problems across 3 calibrated views. So given generic point line image correspondences and the amount specified by the entries in the first 5 columns. So okay, in this column, 3 point matches and 1 point line match. And so on. So then the number of calibrated camera configurations over C that are consistent equals the entry in the 6th column. Okay, so what I'm saying is given 3 generic point matches and 1 generic point line match, there are actually finitely many camera configurations ABC that are consistent. And here that number is 272.
And to find these numbers, you have to actually construct a set?
Yeah.
Or can you
Yeah.
count them a priori faster?
I would love to have an a priori method, but the method here is just finding the set on a generic instance. Okay, so
But these numbers are universal. It's not random data. This is 272.
So there's a Zariski open subset of the image data space, which will be a product of P2 and P2 duals, on which the number of camera configurations equals this number precisely. But there are special configurations, like things coincide and such. But yeah, this is like the analog of 10 for Nister.
And can you find upper bounds for these numbers?
So these, you mean for even special configurations?
Yeah.
So these are upper bounds on the number of isolated solutions for special configurations. What can happen is that you can actually have a positive dimensional solution component in special configurations. But you'll have no more than this many isolated solutions. Okay, so they're a lot bigger than 10, and there are also many, many more cases. So the table goes on. More cases, more degrees, and it goes on. Okay, so these are sort of interesting numbers to look at. I obtained these by computation, but for example, they're all divisible by 8. That suggests a structure to the solution sets. There are also some coincidences between these numbers. Like for example, 160 occurs twice. So 160 is the number of configurations consistent here, this type of image data. And also here.
So do you know why, or is that coincidence?
I don't have a reason why these should have the same number a priori.
There could be coincidence.
Yeah, so there's quite a few mysteries here. So just to clarify, so how many degrees of freedom are there in a calibrated configuration of 3 cameras? So each camera is a rotation and translation with 6 degrees of freedom. And then we're going modulo rotations, translations, and central dilations, which is a 7-dimensional group. So there are 11 degrees of freedom here. And the first 5 columns in the table represent linear conditions of codimension 3, 2, 2, 2, and 1, it turns out. So if I take the first 5 entries in any of these rows and dot with the vector 3, 2, 2, 2, 1, I get 11. And that's precisely what these rows are. Such weight vectors. I'm not going to have so much time to talk about the proof, but the technique relies on an analog of the blue matrices. Here there will be 3 by 3 by 3 tensors. And this construction breaks symmetry between the views, unlike in the 2-view case. Nonetheless, the numbers reported here are true intrinsic degrees for the 66 cases, based on underlying geometry. However, correspondences using types line, point, point, and so on, there are other minimal problems with degrees not covered by this result of proof technique. So here I have only 5 columns, right? But in principle, I should have 2 to the 3. I should have 8 different point line correspondences between 3 views. Okay, so the proof technique, though, is asymmetric. So I only cover these cases here. And let me just remark, these algebraic degrees are complexity measures. Like how many solutions there are. So in terms of the 3D reconstruction, we're interested in small degrees, the smaller entries in those tables, because we don't want to have to sift through 1,000 possible ABC configurations in the reconstruction. Okay, so here's an example to clarify what this means. So suppose we were given the following image data. So this is a point triple in homogeneous coordinates, and then point-point line triples, 4 of them. So I generated these numbers in MATLAB. Say it's a generic instance of the minimal problem 1 PPP plus 4 PPL. So the content of the theorem is that up to the action of G, of changes of world coordinates, there are only a positive finite number of 3 calibrated cameras that are exactly consistent with this image data, namely 160 complex configurations. And for this instance, it turns out that 18 of those configurations are real, meaning that somewhere in the G orbit there's a real ABC. Okay, so for example, this is one real configuration. So in terms of the reconstruction algorithm, we would discard all complex solutions, and then these 18 are competing hypotheses for the configuration of ABC. And to determine which one is the correct configuration, we test against more image data. Any questions about this example? What the theorem means? Okay, let me just quickly go over this in the last couple minutes. So here in 3 views, we can consider not just we don't just consider point matches, but also lines. So for example, the point line multiview variety, PLL, lives inside P2 times P2 dual times P2 dual, and it consists of all points and lines that are consistent under A and B. So it's the Zariski closure of the image of rational map out of the Fike variety of points in P3 on lines in P3. Similarly, we can define a line multiview variety and so on for every column in the table. Okay. So these multiview varieties, characterizing points and lines that are consistent, they live inside threefold products of P2 and P2 dual. We can work out some basic facts about their algebra and geometry, their dimensions, and their prime ideals. Prime ideals here are all given by determinantal equations. Okay, so that's how. So now we can turn this around. So in the previous, to define the multiview varieties, ABC were fixed, and I was asking which points and lines are consistent. We can turn this around, and suppose we observe points and lines that we believe to be consistent. They were detected by software. This point is the top of a tower, and here's an edge that goes to the top of a tower, something like that. So we can turn around the equations on the previous slide and view them as ABC, as the unknowns. Okay, so suppose that the x prime, x double prime, L prime, L double prime are known, the matching points, and we want to determine ABC that are consistent. So we need the minors of these matrices to vanish. So that sets up a polynomial system for ABC. It turns out that those polynomial systems are really, really nasty. So for example, in the example of one given before, we would have like 36 unknown entries, the entries of ABC, and it turns out we would have like 67 chordate equations. And also the equations saying that the left submatrix of A and B and C are rotations. So just a lot of unknowns vastly overdetermined by high degree equations. So the way out, the way to actually solve a single instance of these equations, of these systems, is to use an analog of the blue matrices. Okay, so it turns out that if you fix ABC and ask which point line lines correspond, this is a hypersurface in P2 times P2 dual times P2 dual, cut out by a trilinear form. You can assemble the coefficients of the trilinear form into a 3 by 3 by 3 tensor, and that turns out to be equivalent to ABC up to changes of world coordinates. So the game now is to actually recover tensors, just as Nister recovered blue matrices. And a key thing that makes this a good idea is that the equations, the system of equations on the previous slide can actually be written in terms of polynomials that are linear in these tensor entries. Okay? So passing to the tensors, we can get linear systems in the unknown tensor entries. Okay, and this tells you what those linear systems are. The key thing is they're linear in T. Okay. So now what we do is we consider the algebraic variety of all tensors T that arise in this way. Okay, it's more complex than in the case of Nister. It's 11-dimensional. It's high degree, 4,912. It's the orbit of a P2 under a group action. And so our systems are intersecting this variety in tensor space with linear slices. But they're special linear slices, okay? The coefficients of these linear slices, equations in T, are structured. We take this intersection using numerical. So that's
Thank you very much. Thank you for a beautiful, lucid, insightful talk. Joe will be glad to answer questions in private, and if you'd like to join us for dinner at 6:45 at Evelyn's and you want to, please let me know.